Okay, I'm back. I got to set up here real quick. Okay, excuse me. This chapter is a little bit longer. Excuse me, but shouldn't take too long. All right. Now, this particular chapter, can everybody see that slide okay? Jason, Kehoe, can you guys see the slide I'm sharing? Okay, good. All right. Um, all right. This deals with what is called intermolecular forces. Now, the term inter, I-N-T-E-R, this deals with interactions with other molecules. Okay, as compared to intra, I-N-T-R-A, molecular forces, which deals with the type of bond that these molecules have, be it ionic bond, be it a covalent bond, either nonpolar or polar. Which polarity here is a factor. We talked a lot about looking at the bonds of compounds, whether they're polar or nonpolar. Okay, and this is where it comes to play. Okay, the polarity is a factor, big time, with respect to intermolecular forces. And these kind of things explain why certain things are for example, if I take a cup of water and a cup of honey, and I take them and I empty the cups, obviously we all agree that the honey is going to flow a lot thicker and slower, and the water will flow much quicker. Well, that is because of the intermolecular forces of the honey molecules that are pretty strong, and they attract each other, hold on to each other with a greater force than the water molecules. And these type of forces affect physical properties. And the ones we're going to talk about is one is boiling point. Two is what we call surface tension, and three is what we call vapor pressure. And yeah, one more. There's one more. I'm slipping my mind, but we'll get to it. Okay. Um, so let's talk about it. I forgot to push the record button for the first chapter, so my apologies. This one will be recorded. All right, but again, the chapter we just got done, there is a recording up in the course on the course website. Okay, so intermolecular forces. What we're talking about in this example here, we have two molecules here that are could be anything, could be diatomic molecules, but we're talking about. Let me change my color here because I'm a little bit red. We're talking about the interaction that's occurring right here, denoted by that red dotted line. We got a molecule here and a molecule here, and depending on what type of molecules, there is an attraction for each other. Okay. Um, and so that attraction could be very strong or it could be weak. But the important thing is review about polar and nonpolar bonds in the molecules, because that, to recognize the type of forces, and there's only four forces, but before we can recognize which force is involved with that molecule, you got to refresh your memory about something, compounds that are either polar or nonpolar. All right. Let's take, we all know about the bonds. Okay, let's take this example. We have hydrochloric acid. Okay, this is a covalent bond. Okay, and it's a polar covalent bond. Okay, so any compound with two different atoms, any two different atoms, you have a polar bond, okay? With one exception, carbon and hydrogen. That's a nonpolar bond. Now, if you recall, we drew the arrow. Well, let me draw this arrow like we had before. Okay. And then we had a little plus side over here. Okay. We have a polar bond. The arrow's being drawn toward the chloride because the chloride has a lot more electronegativity. Remember En, electronegativity. Okay. And that was a measure of an atom having the affinity to pull electrons toward it. Chloride's much greater, so we put a partial negative. Remember that little symbol, delta? Sorry, I can't draw it here. We had a partial negative and a partial positive on the hydrogen. Okay? God, terrible with the mouse. Partial negative on the chloride, partial positive on the hydrogen. And you think about it, it's like magnets. You know, this compound has built into it a dipole, two poles, positive end and negative end. And when it meets another molecule, it will line up accordingly, just like magnets will, north attracting the south and vice versa, okay? Resulting in this interaction right here denoted by the blue dotted line, okay? So we have an intermolecular force. That force can be very strong, and like I said, it could be very weak, depending on the type of compound it is. So there's 4 types of intermolecular forces, okay? The first type is called London dispersion forces. Now, these are real simple to point out, to find. Any non-polar compound, the only force they have involved is this, London dispersion forces. So that means if you recall all the diatomic molecules have no fear of ice cold beverage. They're non-polar bonds. The only force they have are the London dispersion forces. The other one is the carbon-hydrogen bond, okay? So the carbon-hydrogen bond and the diatomic molecules all have London dispersion forces, but basically any non-polar compound. There are compounds that have polar bonds, but because the polar bonds cancel each other out, they are non-polar overall. We'll do some examples of that later on, which means the only force they have is the London forces, okay? Second type of force is a dipole-dipole, much like the example we just did right now, where you have HCl interacting with another molecule of HCl, okay? Those are dipole-dipole interactions. Then a real special case is what we call hydrogen bridging. Now, it is another name that you'll see is bonding, hydrogen bonding, okay? That's still used quite a bit. They're trying to get away from bonding and use the term bridging because it's not really a true bond like we think of, like a carbon chloride bond or hydrogen bond. It's really an interaction, but it hasn't changed yet. So they're trying to do away with bonding and use the term bridging, okay? And finally, here, the last one is called the ion dipole. Well, in this case, the thing about this is that, one, you're going to see it in the aqueous system. water, okay? And then some kind of a salt. And any salt, necessarily just sodium chloride, any metal, non-metal combination. Okay, so basically it's the water that has a dipole interacting with the salt, either the positive, full positive, or full negative. Okay, salt meaning, better yet, maybe I should use the term ionic compound. Or salt. Okay. All right, so let's talk about each one individually. London forces, let me get rid of my drawings there, are temporary. Okay. This has to do with attraction between nonpolar molecules. And this happens when they get real close together. Now, a perfect example of this happening is that I'm sure you've seen or even tried taking a balloon and then rub it in on your head, transfer those electrons onto the surface of the balloon, and then bringing that balloon, I wish I had one, and placing it on your chest and have it stick. Well, you ever wonder why it's sticking? Is it some voodoo magic going on? No, it's not. On the chest, on your chest, we have on the surface a lot of electrons, okay? And so when you take that balloon and it's full of electrons, you bring it to the surface of your chest. Well, electrons have a negative charge, obviously. And the ones on your chest are pushed away from the chest and move in, leaving behind a positive area, which then allows the negative of the balloon to attract and hold on, and hence that balloon sticks on. Obviously, it doesn't stick on very long. Eventually, it would fall off because it's temporary and it's not very strong. Okay. So this is essentially what's happening here. Electrons are pushed to one side, thus temporarily creating a partial negative and a partial positive area. Okay. But let me give you some examples in a second. The bigger the nonpolar compound is, the more electrons it has, obviously, thus the more London force. So if we compare the London force, say, fluorine versus bromine, well, the London force for bromine will be much greater simply because bromine is a much bigger compound element. Okay, so this is basically what's happening here. We got the electrons, okay, and they come into play and they temporarily create a partial positive area and a partial negative area to create an interaction there. Okay, weak interaction, but nevertheless an interaction. Now, with respect to dipole-dipole forces, they exist only between polar molecules. They gotta be polar molecules, okay? And the example I did earlier was hydrochloric acid. Here's a diagram of the model of hydrochloric acid. You got the big old chloride, high electronegativity relative to hydrogen. It creates a big partial negative here in this area. Another molecule of hydrochloric acid, there's a big partial positive. So the result is there is an attraction there, okay? Now remember, these are polar compounds. See, so they have a permanent dipole because of the electronegativity as compared to the nonpolar compounds where the polar bond is temporary, okay? Temporary. But that interaction could be pretty hefty, pretty strong. Depends on the molecule. All right. The one thing about London, when we compare London forces to dipole forces, the dipole forces are much stronger relatively to the London forces. London forces are the weaker forces. Then comes a dipole, and then here comes much stronger forces, what we call the hydrogen bridging forces or bonding force. Okay, now these are very specific. Now, yes, they have a dipole in there, but because it involves hydrogen bonded to nitrogen, oxygen, and fluoride, they have this additional force called hydrogen bonding. And only for those examples, when you have a hydrogen bonded to a fluoride or an oxygen or bonded to a nitrogen, okay? Those guys are involved with hydrogen bridging force. You can see here this similar aspect. This is a very strong interaction here between the partial negative of the oxygen and a partial positive of a proton on another molecule of water. In the diagram to the right, you can see there's a lot of force going on there. Okay, a lot of force. In this case, hydrogen bridging force. Okay, this is the strongest one. It's much stronger than dipole, which is much stronger than London forces. Okay, but they are weaker than the actual bonds themselves, like the actual ionic bond or covalent bond. Okay, these forces are not bonds, they're just very strong interactions. Now, with respect to the last one, it's called the ion dipole force. Okay, as I mentioned earlier, you need some type of ionic compound and aqueous system. So that's what we're going to be talking about for Chem 130 is simply aqueous systems. You can see here from the diagram how that sodium ion is basically surrounded by water molecules. The sodium with a big old plus, a full-fledged positive charge, surrounded by the partial negative on the water molecules. And you can also imagine if this was sodium chloride, the sodium chloride will be on the outside here. I can draw it because the chloride has a negative charge, and there'll be a big interaction with the partial positive side of the water molecule. So it's pretty strong all the way around. Okay. Now let's summarize some things. Bonds. Okay, we're going to have ionic bonds. Refresh your memory on those. That is a combination of a metal and a non-metal. Second of all, ionic bonds have a full-fledged charge, either a full-fledged positive or a full-fledged negative. Now, polar covalent bonds, that's the sharing. Covalent bonds are the sharing of electrons. If the sharing is unequal, because one element is stronger, has a higher EN, electronegativity, then we're going to have an unequal sharing, which results in a polar covalent bond. If the sharing is equal amongst the two elements that are bonded, then we have a non-polar covalent bond. Okay, so all the diatomics and a lot of compounds in which the polar bonds cancel out will be non-polar. Okay, forces. We got the London forces that applies only to non-polar molecules. So every non-polar molecule out there, the only force they have are London forces. The dipole, the requirement must be that it's got to be a polar molecule. Okay. Now, with respect to hydrogen bridging or bonding, it is hydrogen bonded either to nitrogen, oxygen, and fluoride. And then finally, the ion dipole force, that is when you have an ion a salt of some sort interacting with a polar molecule, which for us would be water. Okay. All right. So question here is, first we're going to determine the polarity of the molecule. Okay. And then from that, once we know the polarity, then we will know what is the strongest intermolecular force in that molecule. Okay. Now, the first one, carbon dioxide. This is, in this part, this is where the Lewis dot structures, remember those? When we were writing formulas, and then from there determining where the molecule is polar or nonpolar. Okay, this is what comes into play. So you got to refresh your memory. If you're not sure whether something is polar, then do the Lewis dot structure, and that's going to give you the information. Okay. Remember when we did those, that any central atom has a lone pair of electrons, automatically is a polar molecule. You could have one lone pair or two lone pair. When we did carbon dioxide, we came up with this structure, if you recall. Okay. Yep. All right. We had that structure where we had a double bond between the carbon and the oxygen. There was a dipole going from carbon to oxygen in opposite directions. Okay. That caused that dipole, even though they had polar bonds, they canceled out. Because the one to the right cancels out the dipole going to the left, resulting in a non-polar compound, which carbon dioxide was non-polar, even though it had polar bonds. Therefore, being non-polar, the only force it has are London forces. Any IMF interaction is simply London. Okay. If you look at the next one, PF3, it is in group 7. Group 5. The central atom is phosphorus, group 5. Okay. If you do the Lewis dot structure, you're going to end up with a lone pair of electrons on phosphorus, which tells you automatically, I got a polar molecule. Okay. Now the question is, obviously it's not London forces as far as IMF, and it can't be hydrogen bridging because there's no hydrogen involved here. Second of all, it's neither nitrogen, oxygen. Okay, it is fluoride, but there's no hydrogen. So the only thing left is dipole forces for that molecule. Okay. We look at HF. HF is polar, no question about it. Two dissimilar atoms, very polar. Okay. Second of all, it has hydrogen involved, and it's attached to the fluoride, which is one of the NOS, nitrogen, oxygen, and fluoride. So its force is hydrogen bridge forces. Okay. Now we look at the next one where all we see is carbon and hydrogen. Remember I talked about those carbon hydrogen, they're called hydrocarbons. If that's all we see, all nonpolar, totally nonpolar compound. Okay. Therefore, London forces are the ones involved. And then finally, Ki, we got potassium iodide, ionic compound, aqueous, water. Okay. So it's an ionic compound in polar water. So its interaction is simply the ion dipole. All right. Now, I kind of need to talk a little bit about this, not to necessarily having to memorize everything, but what's going on here is this. It's related to what's called Coulomb's law. And those are interactions between two charges. And what they're saying here is that the attraction between two charges is proportional to the magnitude of the charge, okay? Proportional, meaning that it's two variables, A and B. If one variable goes up, the other one goes up accordingly, okay? That's what we're talking about, proportional or directly proportional. And also it's inversely proportional to the distance squared between the two charges, all right? So what does that mean? Inversely proportional means that one variable goes up, the other one drops, okay? Inversely proportional. But it drops even further because it drops to the distance r squared, okay? And I'll run through an example here in the next slide. And so we're talking about this interaction here. And you probably see it or done something similar. You probably, taken two magnets and bring in the north or the south together. You can feel that force of repulsion as you bring them closer together. The closer you get them together, the stronger the force of them trying to repel, okay? And then as you pull them apart, you can feel that force lessen very drastically. You pull them apart very little, that force really is suppressed. And that force is suppressed through the square of that distance between them. So it's very, very, very rapid as far as the force dropping. And this equation is what all that is saying. Now, K is a constant, so we don't have to worry about it, okay? It's always going to be the same. Q1 and Q2 are simply the charges, okay? So let's say, for example, we got Q1 is equal to 1, Q2 is equal to 1, K is constant, okay, whatever that value is, and R is 1 unit of distance apart. So we plug in the numbers, you get 1 times 1 divided by 1. Obviously, force is equal to whatever K is, okay? Now let's take that same scenario and now double R. It went from 1 to 2. So now it's 2 units, okay? Q1 and Q2 remain 1. R now goes to 2. The square of 2 is 4. Okay, so now it's 1 over 4. So by just doubling the distance from where it was initially, you have reduced that force by a quarter. That's how drastic that force is dropped. And that's basically what they're telling you there. That's what we would like for you to take away, okay? You reduced it by a fourth. If you triple that distance, 3 times 3 is 9. You have reduced that force by 1/9. All right. So let's go run through some questions and see if we can figure out here what they're talking about. It says here, what holds the atoms together in one ammonia molecule? So they're talking about one ammonia molecule. We're not talking about intramolecular forces. We're talking about intra. What is holding the atoms together? Okay. Well, that's the bond. It is a polar covalent bonds that are holding holding the molecule together. Okay. Here it says, what is holding the sodium ions in water? Okay, we're talking about sodium ions. We're talking about water. That's that force number 4 we talked about, and that is the ion dipole force. Okay. Next question, what is holding 3 hydrochloric acid molecules together. So now we're talking about the molecules interacting with each other, okay? So we have to first determine, is HCl polar or nonpolar? Well, HCl is very polar, okay? Therefore, it has to be one or two choices, not London forces because it's polar. It can't be hydrogen bridging because it's hydrogen bonded either to nitrogen, oxygen, or fluoride. So the only choice you got left is dipole-dipole, okay? Next one says, what is holding the ions together in salt, sodium chloride? No mention about aqueous systems. They're just talking about solid sodium chloride. So the only thing you have, we're talking about the bond. In this case, the ionic bond. It's an ionic compound. Okay. Now the question, next one, what is holding 4 H2O molecules together? So we are talking about molecules interacting with each other, okay? And so it's not London forces. It's not ion dipole because there's no ions involved here. So it's got to be either hydrogen bridging or dipole. Well, the fact that you got hydrogen bonded to oxygen, automatically hydrogen bridging. Okay. Next question, what holds the nitrogen gas molecules to each other? To each other being the key word, IMF interactions, okay? Find out nitrogen. Nitrogen gas, nonpolar. It's one of the diatomic molecules, nonpolar. The only force involved there are London forces, okay? Now, what is holding the oxygens together in an oxygen gas molecule? Again, we're talking about what's holding the oxygens together. That must be a bond. What kind of bond? Well, we know that O2 is nonpolar. So it's a nonpolar covalent bond, okay? And then finally, the last question, what is holding 2 ammonia molecules together, okay? IMF interaction, we're talking about 2 molecules together, okay? Ammonia, you know, we used it quite a bit, lots of times, so you just refresh your memory that its formula is NH3, okay? Very polar, it's got a lone pair of electrons in the central atom, plus hydrogen is bonded to nitrogen. We have hydrogen bridging forces, okay? Hydrogen bridging forces. All right, so this kind of summarizes the flow chart of the forces involved. You know, when we talk with covalent, if it's nonpolar, then the only force is London forces. If it's polar, it's either going to be dipole or hydrogen bridging. And it can only be hydrogen bridging if hydrogen is bonded to nitrogen, oxygen, and fluoride. And if the question talks about a polar solvent like water, and then we're dealing with an ion dipole interaction, okay? So with that information, once we can determine what force is involved, we can look at these properties and compare 2 different compounds and determine which one would you predict to have either a higher vapor pressure, boiling point, surface tension, or viscosity. Now, what is vapor pressure? We all are familiar with this. You take a soda pop, you got it capped, you drank some, so it's empty on the very top, right? Nothing but gas up in the very top. If you were to put a pressure valve on the very top, you will get a pressure because of the gas molecules that are in the empty space. That is called vapor pressure, okay? Now, you might think about this for a second. Given what we've been talking about as far as the strength of the forces, if the liquid, if those forces are very strong, they're not going to allow a lot of gas molecules to go into the vapor. Hence, if you have very strong intermolecular forces, you're going to have less molecules in the gas phase. Hence, vapor pressure drops. If the intermolecular forces are weak, then more molecules are going into the gas phase and the vapor pressure goes up. Okay? Boiling point. Boiling point is that temperature at 1 atmosphere that a liquid starts to boil. For example, water at 1 atmosphere boils at 100 degrees Celsius. Okay? And if we were to compare that boiling point to, let's say, ethanol, ethanol is a alcohol, which also has the same type of forces involved, intermolecular forces, but alcohol boils around 78 degrees Celsius. So that infers that the intermolecular forces of alcohol are much less, okay? Because it doesn't take much for heat or energy to cause the liquid molecules to separate and go into the vapor phase. All right. Now, surface tension, that's how well, say, a drop of liquid interacts with the surface. You're all familiar with, you wash your car and you put water on it, it beads up. Okay, that's surface tension. Some of these molecules who have strong intermolecular forces, when they put them on surfaces, they beat up very strongly. Others spread out, okay, because their forces are less, okay? And then finally, viscosity. And that's just a measure of how thick, how it flows. And I use the example of honey and water, okay? It's the race. Flip the cup over. Obviously, honey doesn't flow as much, as quick, and water does, because the intermolecular forces of the honey molecules is much stronger than the water. Now, how can I make that honey flow a little bit more? I add heat. If I heat up that honey, it's going to flow quicker, because that heat, what it's doing is breaking up the intermolecular forces of the molecules, separating them. So now the molecules the honey is able to flow much easier. Okay. All right. So vapor pressure, I just talked about that. Okay. Vapor pressure is just a measure of a closed container of liquid going into the gas phase. It has to be closed, obviously. And you know what happens, a lot of liquids, you keep the cap off, it evaporates and you lose liquid, so forth. So we're talking about a closed container, okay? Now, if you have a strong IMF, would one predict a higher or lower vapor pressure? And the answer is lower, okay? Because the stronger attractions will prevent molecules to easily escape into the vapor phase or into the gas phase, okay? Good example right here, okay? By looking at the diagram, they ask you which is the weaker IMF, or that would be A, in which will have the higher vapor pressure. That will also be A, okay? Because if we look at the molecules that are in the air in vapor phase, there's quite a bit compared to B, okay? That suggests that for A, these interactions, IMF interactions here, are much weaker than in B, okay? And therefore, the molecules in B are held closer and tighter together than A, and therefore less molecules go into the atmosphere. Yeah. Boiling point. If you have a stronger IMF, would one expect a higher or lower boiling point? Well, again, you will have a higher boiling point because, again, the IMF interactions between molecules is very strong, and it would require more energy to break up that interaction, okay? All right, so also means the melting point. That's that temperature in which a solid starts to melt into a liquid. That also too would affect, the melting point would be affected by IMF interactions. Surface tension, stronger IMF results in high surface tension. Same reasoning again with the molecules interacting with each other. All right, and this is an example here. We got A. Okay, A has the higher surface tension because it's beating up much more, because the IMF interactions for A are stronger, so the molecules are being held much closer together, and because much stronger compared to B, where the liquid kind of just flattens out a little bit relative to A. Now, when we do comparisons, we can't really give you absolute values. What is the boiling point for a particular compound? Now, all we can do at this point from what we've been studying so far is give you relative and predict, well, this one will be higher, this will be lower than something else, okay? None of the compounds. We're doing a relative kind of comparison. Viscosity, oil flows slowly, high viscosity. Vodka fairly rapidly, low viscosity, okay? Again, stronger IMFs will have a higher viscosity, again, for the same reasoning. All right, so let's compare two compounds here, ammonia and fluorine. All right, well, first of all, we need to write the formula, okay? And so ammonia is the formula NH3, and if you do the Lewis dot structure on that, guess what? You get lone pair of the nitrogen. What does that tell you? Very polar. Fluorine, diatomic, okay? Nonpolar compound. Being nonpolar, the only force involved here is London forces for fluorine. Ammonia, it's polar, but it has hydrogen bonded to nitrogen. So it has the strongest force, the hydrogen bridging force, okay? So once we identify what force is involved, we're able to answer some questions relative. And here, which has a stronger IMF? Well, ammonia, because ammonia has the IMF and the hydrogen bridging force, which has the lower boiling point. That would be fluorine, because it has the weaker force, the London force, okay? Which is polar. Well, we talked about that. Ammonia obviously is the polar compound, okay, compared to fluorine, it's diatomic, it's nonpolar, and which would have the higher vapor pressure. That would be the one with the weaker force, which would be fluorine, okay? And which would be, if these were liquids, which would be the least viscous? That would be fluorine, again, because of the weaker forces. And more surface tension, ammonia. Ammonia would have the greater surface tension, again, because of the stronger IMF interaction, okay? And that's how we can compare and contrast. Just, it's all we're doing, kind of which one is higher, which is lower scenario. We can't really determine absolute values, okay? So to kind of summarize, as we increase the IMF, our viscosity increases, okay? Our boiling point increases. Our surface tension increases. And the only thing that decreases is the vapor pressure, okay? Simply because the intermolecular forces are strong. As we increase the force, more molecules are held together in the liquid phase, and less of them are going into the vapor phase, and hence less vapor pressure. Now, these questions are asked in this manner, but they could reverse the question. Instead of saying increase, they could have said as IMF decreases, what happens to viscosity? So be able to answer the question depending on how it's asked. Very briefly, going to talk about waters. Water is kind of very special. It has some interesting properties. Going back to the Lewis dot structures, we determined that it had the bent geometry, and its bond angle was much less than 109. Water is very polar. It will dissolve literally all ionic compounds. Some of them are totally dissolved, and some of them are weakly dissolved, but it will dissolve a lot of stuff. It has very strong hydrogen bridging force between them. Okay, very strong. Okay, very polar, very high IMF, low vapor pressure. The boiling point of water is 100 degrees, and the melting point of water is 0 degrees. That's the temperature that ice becomes liquid at 0 degrees. It has a very high surface tension. And the unique property about water is that when it freezes, it expands. And hence the density of ice is much less than pure water because of the volume increase. Recall the density is grams over milliliters. And so for 1 gram, the volume may increase to say about 1.1. And so now it's 1 divided by 1.1, which gives us a density of less than 1, about 0.9. So it floats, right? So very unique property. Also, when it does freeze, it does give us this very interesting hexagonal shape, which tends to be kind of nature's shape, hexagonal. There's a lot of examples of a hexagonal shape of solids. Anyway, let me go here. All right, so we got to briefly talk about the heating curve because it's related to IMF interaction. But here we have a typical heating curve. So you can see in the bottom left corner, we begin as a solid, okay? And as we add heat this direction, this is a graph of adding heat or energy, and when we have the temperature go up in this direction, okay? So it's heat versus temperature. So we start as a solid, temperature goes up as we heat it, and then we hit a plateau, okay? We continue to eat heat. There's a lot of heat going into the system, but we hit a plateau, okay? Then at a certain point, depending on the compound, the temperature rises again until we hit another plateau. And again, we're adding energy to it, but regardless of the amount of energy we put into it, that temperature remains constant. So we get a second plateau. Eventually, there's a point where then the temperature increases and everything's in the gas phase. So at the points of rising, all here in the bottom left, it's all solid. And then when the temperature rises, like I'm showing here, it's in the liquid phase. And then finally over here to the far right, it's in the gas phase, okay? Now, we can take an example here. And this could be water. It's a good example. We start off heating the material, and as we rise, it's all solid until we hit that plateau where we have a mixture of solid and liquid, okay? And so the reason we have a plateau here is because all this energy we put into the system is being used to break up the intermolecular forces of whatever in this case, of the ice cube going to liquid. They're very strong forces in the solid, and it's water. And so all that energy goes into breaking up that interaction. And hence our temperature doesn't increase. It stays stable until such point that all of it now is liquid, and then we got another rise until we reach the boiling point. In this case, the water, 100 degrees. So this is 100 degrees for the boiling point, 0 degrees from the melting point. And then we hit another plateau. Okay. At this plateau, liquid is being converted to gas. And no matter how much energy we put into it, until all that liquid is converted, there's no increase in temperature. And so once you get water boiling, if you think you're going to get it to boil more or get hotter, forget it. Just turn your heater, turn your burner down, get it to boil, because no matter how much more temperature or heat you put into it, your water is going to stay there at the plateau until such time that all the liquid has been converted to gas, and then obviously you get an increase in temperature. Okay, so this is a typical heating curve for water. So where we hit two plateaus, the plateaus is where there is conversion of one phase to the other phase, and the rises are where we have either pure solid, liquid, or gas. Okay. All right. That being said, so during the phase changes, the temperature remains constant. Okay, because all that energy is being used to break up the intermolecular forces. Not breaking up the bonds, mind you. We're just breaking up the forces between the molecules. This is a physical change we're talking about, not a chemical change. Okay, and the way the graph showed, we're going from left to right. That's by adding energy into the system. You can reverse it, go the opposite direction. We're taking energy away from the system and bring it back to gas, liquid, and solid. Same scenario. Okay. That being the case, guess what, lady and gentlemen, we are done with chapter 14, and we're almost done because chapter 15 is extremely small, maybe about 10, 11 slides. Let me stop for a second. Okay. So, does anyone have any questions? Okay. I'm gonna head back to the beach here in a minute. Like I said, I just upgraded my laptop, so I got to play with some toys here. I hope you can hear me okay. There was no hesitation or anything like that. All right. So, if you don't have any questions, we're done, and I'll see you next Friday, and or you can